In this video, we're going to take what we already know about transformations and apply them in the context of matrix equations. So we can achieve exactly the same key skills that we looked at previously through the application of matrix transformation equations. So by the end of this video, hopefully we should be able to describe a sequence of transformations that have occurred to a pre-image in order that it maps onto the image. Now, the difference here is that the way these transformations might be presented is in a matrix equation. Further to that, if we're given a series of transformations, we should be able to find the image of a function or a graph that has undergone those transformations. Now, the way we're going to do that is to use a different method, which is using matrices. So first of all, it's important just to reiterate what we already know. If I had the graph f of x, and I wanted to say that it mapped onto this thing here, let's remind ourselves what we're saying. The A is referencing a dilation from the x-axis. So we'd say it's dilated by a factor of A from the x-axis. You might remember also that if it is dilated by a factor of A, and that A value is less than 0, so if it's a negative number, we would say it's reflected about the x-axis. So next we can deal with this letter n. Now n exists inside the function. And so this is really, if it was negative, we'd be saying that this is reflected about the y-axis. And it also represents a dilation from the y. So if we're looking at something inside, we might think of it as a dilation or a reflection from the y. That's the really important bit, why I keep saying it. So if we're reading this correctly, and we see that there's some number inside the brackets, inside the square root, inside the truncus, inside the function itself, then what we need to say is that it's dilated by a factor of 1 on n. Remember, when we're looking at the image as a function, the dilation factor from the y was actually 1 on n. Now, to see this in more detail, we'll have to go to look at the previous video. Also, if n is less than 0, we would say that this is reflected about the y-axis. Now, giving ourselves a little bit of room here, we can see that if we had minus h, so it's a bit like saying it's the opposite of what's inside the brackets, you may remember from last video, then we would call this a translation. Now remember, it's the opposite of what we see, so minus h is translating in the positive direction, and furthermore, it's the positive x direction. This is the thing that translates left and right. So we would say that this was translated, or there's a translation. So let's actually use the same tense. Translated h units along the positive x direction, or in the positive x direction. Finally, the last type of transformation we look at is this plus k. And so we don't have to worry, this sits outside the function. Don't have to worry about changing the sign. This is just translated k units in the positive y direction. So these are the functions that we know. We're going to look at how they exist as a matrix equation. So how we might be able to represent the exact same transformations, though this time using matrices. So here, what we've done is we've started to write out a matrix equation. What we're saying with this t is we're saying the transform, or rather the transformation. So it's a bit like calling it a function that transforms x and y. Because we're trying to transform both things here, we can't simply write this as a scalar. We can't just use x or use y. We're using the array, the matrix, the list, however you want to think of it. We're using the array x and y. So we're transforming both coordinates, or both components of each coordinate, throughout the whole graph. So the transform of x and y. Now, the next bracket here, we can think of as our dilation. Now, if this is a dilation matrix, remember that it's also the reflection matrix too. Now for the purpose of this video, we're going to imagine that the leading diagonal is made up of zeros. Now, being the dilation or reflection matrix, you can imagine that we're dealing with A and N. And the good news here is that what we see in the matrix is exactly as we describe it. So if I had an N there in the top left component, that would be multiplied by the X. And so we would call this a dilation of factor N. We don't have to worry about inverting this, about taking the reciprocal. This is a dilation of factor N from the y-axis. I'm hoping you'll remember from last video that if we're dilating from the y, then we're multiplying or changing all of the x values, so in each coordinate. So here, dilating by a factor of n from the y makes sense that when I multiply nx plus 0y, I'd be changing x. Further to that, you may notice that if n's a negative number, so if n's less than 0, then we are reflected about the y-axis. So this is a reflection in the y-axis. That's how we describe that. So our A goes in the last position of the matrix. Now this would be the thing that's multiplied by y. So this is dilation of factor A. And this one's from the x-axis. Also, if A is less than 0, then we would be reflected. Let's just fix that up, sorry. Now, because we're changing all the y values, if we were negating them all, we'd be reflecting about the x-axis. About the x-axis. So this is my dilations and reflections, and this is a matrix that would be multiplied by x and y. If we're adding something, you may have already guessed that we'll be adding h and k. Now the good news here is that I don't have to worry so much. If I'm plus h, then that's what I'm translating in the positive direction. If I was minus h, I'd be translating in the negative direction. So there's no need here to think, oh, I've got to change the sign. It's simply stated as we read it. So this is what we can see with our matrix equation. If we looked at it this way, where we had a dilation and we also had a translation matrix, then what we're saying is we're going to multiply x and y by something. We're going to add h to the row x and k to the row y, and ultimately we're going to have a new set of x and y. We'll call it x dash and y dash. We're not saying the derivative of x or y, so you may have seen that dash notation last year, but what we're saying is new x and new y. So in summary, imagine any coordinate x and y, so that's our little matrix here, represents the coordinate x, y. We're going to undergo these transformations, and that could be a series of dilations, reflections, and translations. And at the end of the day, I'll have a new point, which we'll call new x and new y. So this is how we might describe a sequence of transformations, and I'll show you what that looks like in comparison to the functional notation. So we can actually see some advantages to using the matrix transformation method. Rather than having to look at a function and infer all these things about n and h, here we can read it exactly as we see it. So whatever I read in there, that is the dilation factor. However, if it was inside the function like f of 2x, I'd have to describe it by its reciprocal. So I'd say it was dilated by a factor of a half, or 1/2, in that example of f of 2x. Further to that, h, we have to often do we often say do the opposite of what you see in the brackets. Well, here I don't have to worry about. x plus h is the positive direction. So that's why we look at matrix equations. So I'm going to flick to some examples now and see if we can put this in a practical context. So I'll give you a matrix equation and we'll try and find the sequence of transformations that it represents. So in this example, we're given the following matrix equation and we're saying that it was applied to the graph y equals x cubed. Now, we're asked to find the rule of the transformed function, so we need to actually find the rule and describe the sequence of transformations. Now to do this, I'm actually going to describe the sequence first. So let's look at what we see very initially. We've got this number 2. Now it's in this position, which would be applied to the x, and so we know that this must be my equivalent n. That -1, remember this is our dilation and reflection matrix, that's the equivalent of A. The -4 is going to be my H equivalent, and the 0 here would be my K. So let's look at describing that very first n. It's a 2, I don't have to worry about taking its reciprocal, and so I'd say this has been dilated by a factor of 2 from the y-axis. We can see that A is a -1, and so we describe this as a reflection about the x-axis. There's a -4 here as our translation, and so this function y equals x cubed has been translated 4 units in the negative x direction. So we need something that goes in the negative x direction. So let's see if we can take this information and apply it to the graph of y cubed. Well, if I started with y equals x cubed and then I dilated by a factor of 2, that would be y equals something times x cubed, and the something has to be a half. The reciprocal of a half is 2. If I was reflecting about the x-axis, well, that would be a negative out here. And if I was translating 4 units in the negative x direction, then what I'd need to do is now put that +4 inside the brackets here. Still needs to be over 2, so I might rewrite this final step. Minus x over 2 cubed, but now this has to be +4. Now, if I imagine this and I took the half out as a common factor, I'd still have a translation of 4, and that's how I know that I'm correct. So I described the sequence of transformations from a given matrix equation, and I found the image of the curve using what I already know. But there's another way to actually use matrices in order to find this image, and we're going to do that now. So all I've done here is I've taken this equals nu x and y and put it to the end. Let's start by solving this matrix equation. Well, when I multiply the top row by the first column, I'll have 2 times x plus 0y. So this matrix will be 2x. If I multiply the bottom row, 0 times x disappears, -1 times y becomes -y. And so now I've got this, and I still need to add -4, 0, and I know that will equal a new x and a new y. In order to add matrices, that's a lot easier. I just need to say 2x minus 4, -y plus 0. So this is 2x minus 4 on the top, and it's -y, and that equals new x and new y. So now that I've got this, let's look at what it means to be equal. I'm saying that the top row, this top row here, is my new x. So 2x minus 4 is my new x. And negative y, this bottom row, is my new y. Now, once I've done this, so I've multiplied and added, in other words, I've resolved the matrix equation, I can then equate my top line to my new x, my bottom line to my new y. The final step here is to solve for x and y. Let's get the x and the y as we know it in terms of only my new x and new y. So this will be 2x plus 4. And we're dividing by 2. You might recognize that. Here I'd be taking the negative 1 over and saying y equals negative y. Now once we've done that, you'll see that there was a method to our madness. There's a reason why we did it. Once we have x and y in terms of x dash and y dash, we just sub this into our pre-image. So remember that our pre-image was y equals x cubed. And I'm saying that y is actually negative y, or negative new y. So let's replace this with negative y. Now that has to equal x cubed, but remember that x is actually x dash plus 4 on 2. So it's actually x plus 4 on 2. And because it was x squared, that's x cubed rather, that's still cubed. Now the final step is to multiply by a negative, and so we can see that y is negative x plus 4 on 2 cubed. And that's exactly what we got with our previous method. So to summarize the matrix method, we can describe a sequence of transformations using our understanding up here of n, a, h, and k. We need to first resolve the matrix equation, equate whatever the top row is up here to the top variable, my new x, the bottom to the bottom. So in other words, we're going to equate x to x dash, y to y dash. Once we've done that, we can solve for x and y respectively, and then it's just a matter of subbing it into the pre-image. So let's see how you've understood these concepts thus far. For example 2, you're being asked to find the matrix equation that determines the following translations. So you don't need to solve anything, you just need to find the matrix equation. So there's a thing that you need to find. And the context that you've got to do it is listed here. Now, I'll give you one hint. It's going to look like this. The transform of xy will be equal to a dilation matrix. It's going to be times by x and y, and you're going to add your translations. Finally, that will equal new x and new y. So pause the video, give this question a go, and we'll go through the solution in a moment. We're first asked a dilation of factor 3 from the y. So these are all kind of the critical terms in that sentence. Well, from the y appears here, and it says it's 3. Remember, I can write it exactly as it appears. I'll always have 0, 0. I shouldn't say always, but for this context we will. And we'll go through what happens in a later video when that's not the case. Then we're told we've got a reflection in the x-axis. So it's a reflection, so that tells me -1, and it's in the x-axis, so that's down here. Now something you might have missed is this phrase followed by. So what we're saying is that this happens as a sequence, it happens in order. We've had a translation of 1 unit in the positive x direction. So 1 unit, positive x direction, it's +1. 2 units in the negative y, so 2 units in the negative y would be minus 2. And so you can see that we've now formed an equation. It is a matrix equation, and it determines the following transformations. In the previous example, I mentioned the phrase followed by. So let's have a look, because it's here again, followed by, but let's have a look at what happens when we've got things in a weird order. So it is a transformation matrix of x and y. And at the end of the day, it will still equal a matrix for new x and new y. However, we've started with a translation of 1 unit right of the x-axis and 2 units up. So we started by saying xy plus, now 1 unit right, so that's 1 and 2. After that happened, we then have to dilate by a factor of 3 from the y-axis and then reflect in the x-axis. So you'd be forgiven for thinking, well, now I'll multiply by my dilation matrix. But that would actually be incorrect. Now, when we get to matrices, you'll learn that A times B is not B times A. So when you first learned matrices last year, I'm hoping that you'll remember that the order really matters. So a 2 rows by 1 column, a 2 by 1, cannot be multiplied by 2 by 2. And so I need to know that dilation always has to happen first. So this will be my dilation matrix. Then I'll multiply that by xy plus 1, 2, and that'll equal x dash, y dash. So this is a very niche kind of question. It's very rare, but if it did happen, it's important to know that this phrase followed by has a really important meaning. So as a factor of 3 from the y-axis, so a 3 will go up there, and reflection in the x will go here. In this example, we're told that a transformation is defined by the matrix here. So there's no translations, there's only a dilation. We're being asked to find the equation of the image. So we're finding the equation of the image. Now, it's the image of this graph. So this is not a very simple pre-image. So there's a little bit to this, I suppose, this problem. Now, this is a great one to do with the matrix method. You need to first apply this transformation. So I'll help you with that now. Transform of xy is equal to 2, 0, 0, negative 3, xy, and that will be new x, new y. See if you can pause the video here and give this a go. Remember that your goal is to find the image of the graph of this equation. It's a very poor sentence, but find the image of this equation. Okay, I'm hoping that you paused that and gave it a go, and I'll go through the solution now. If we apply this dilation matrix, we'll get 2x minus 3y. Remember, the zeros will cancel the other variable. So 2x minus 3y, that matrix is equal to x dash y dash. So let's equate them. I'll do it in a different color because it's a different step. We resolved the matrix equation. We equate 2x to x dash minus 3y to y dash, and we'll solve for the variable x and the variable y. So here I divide both sides by 2, and x equals x dash on 2. Divide both sides by negative 3, and y equals y dash on negative 3. Once I've done this, I can sub these new terms into my pre-image. So yes, y equaled x squared plus 2x plus 3, but now this y is y dash on negative 3. And this x has got a little bit of work to do because it's x dash on 2. Now, if I simplify this, and remembering that this is actually negative 3, if I simplify this, I'll multiply everything by negative 3 to find that y dash is equal to negative 3 x on 2 squared plus 2 x on 2 plus 3. Remember, if I'm multiplying by negative 3, I'm multiplying the whole thing. So y dash is negative 3 x squared on 4, because x on 2 squared, square the top, square the bottom. Now 2 times x on 2 cancels. Negative 3 times x would be minus 3x. Negative 3 times 3 is minus 9. And so I don't want to have this y dash. That's not good practice when finding the image of a curve. So to give my final answer, y equals negative 3x squared on 4 minus 3x minus 9 is the equation of the image of the graph. So in this example, we know that a transformation is defined by this equation. The image of the curve with this equation under this transformation t has that equation. So this is a real mouthful to try and get your head around. What we're saying is there is a transformation. This is one of the things. So in red I'll put my things. There is a transformation. The image of the curve with this equation under that transformation is that. So this is my image. The image, context, 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 is. And so the pre-image is here. Now that's really, really poorly worded, but very, very indicative of what we might find in the exam. The image of the curve with this equation under that transformation has this equation. Ugh. What are we asked to do? We're asked to find the values of A, B, and C. And so if I apply this transformation to that pre-image, I'll get this image. Once I've got that, I'll have to put it in standard form, and that'll allow me to infer what A, B, and C are. So pause the video, give this a go, and then we'll do the solution that you can refer to if you get stuck. Okay, let's start by resolving the matrix. 3 times x and 2 times y gives me 3x, 2y, plus negative 1 and 4 will equal new x and new y. 3x minus 1, so that top line, must therefore equal x dash. And 2y plus 4, that bottom line, must therefore equal y dash. If I add 1 and divide by 3, then x equals x dash plus 1 on 3. If I minus 4 and divide by 2, then y must equal y dash minus 4 on 2. Now we can take these new x's and new y's and sub them into my pre-image. So instead of y equals 2x squared plus 1, we're going to replace that x with x dash plus 1 on 3. And we're going to replace this y with y dash minus 4 on 2. If I resolve this, so I square the top, square the bottom, I've got 2x plus 1 squared over 9, because that's the square of 3. This is plus 1. And on my left-hand side, I've got y dash minus 4 on 2. If I multiply everything on the right by 2, y dash equals 4 over 9, x plus 1 squared, plus 2. And if I add that 4, I'll have a plus 4. So we can see here that the final image, y is equal to 4 over 9, x plus 1 squared, plus 6. However, the question was more difficult than that. It didn't say find the image. Remember, it said that the image has this form, which is in standard form, find a, b, and c. Now, in order to do that, I need to fully expand out this expression, and then a will be whatever the coefficient of x squared is. B will be the coefficient of x, and c will be whatever the constant term is. So, expanding out x plus 1 squared, x squared plus 2x plus 1. Square the first, square the second, twice the product in between. So that's a difference of squares. If I multiply the 4/9, then I get 4x squared on 9 plus 8x on 9 plus 4 over 9. Now I've got to add 6, but as a fraction of 9, that's 54 on 9. And so we're nearly there. Y absolutely is 4x squared on 9 plus 8x on 9 plus 58 on 9. But I don't need to find y, I need to find a, b, and c. Well, my a is that coefficient, so it's 4 over 9. My b is this coefficient, which must be 8 over 9. And my c is the coefficient of x to the power of 0. It's the constant term, which is 58 on 9. So this is about as complex as these kinds of questions get, but I promise that with a bit of practice, you'll really get this, because you'll see that all the questions are in the same format. Start by finding what are the things. What is the question asking me to do? So really, what is the question? You can always look for command words here. Find, solve, evaluate, simplify. And once you've done that, try to link it together with a bit of context. What we did here is we applied the transformation matrix to this pre-image. So that meant multiplying out and adding. So it meant resolving the matrix equation, equating x to x dash, y to y dash, so I had to solve for that to happen, subbing it into the pre-image, expanding it out totally, and equating coefficients. This is a much more straightforward approach, or straightforward question I mean to say. We're being asked not only to just find the equation of the image, and it's the image of this pre-image, but we're also being told that we need to use the matrix approach. We've got this as a bit of context. That's my sequence of transformations, and it is a sequence, so it does have to be done in order. And it says the graph of 1 over x is transformed. So that must be something happened to it. It is, or it was transformed. So something is happening to it. It has to be the pre-image. Let's see how you go with this, and we'll do the solution in a moment. So I'm hoping you've paused the video and given it a go, and let's go through the answer. A dilation factor 2 from the x and 3 from the y. Well, that means 3 and 2 must be in these positions. A reflection in the x-axis, well, that happens down there. And a translation of 3 units in the direction of y, -2 along the x-axis. That's not a great way to write that. We should have said 2 units to the left, or 2 units in the negative direction. But it does help us because we're just always adding 3 units in the y and -2 in the x. So this was my matrix equation. I know it equaled x dash y dash. If I resolve this matrix, 3x minus 2y, I'll get 3x minus 2 equals x dash. And negative 2y plus 3 equals y dash. If we solve this, then x is equal to x dash plus 2 on 3. And y is equal to y dash minus 3 on negative 2. Let's just keep the negative 2 there for now. If we replace our pre-image with these variables, then y doesn't just equal 1 on x, it now equals 1 over x plus 2 on 3. And y is y dash minus 3 on negative 2. Now, if I'm taking 1 over a fraction, that's another way of saying just flip the fraction. So this becomes y minus 3 on 2 is equal to 3 over x plus 2. You'll notice that I got rid of the y dash. I don't need that anymore. If I multiply by negative 2, sorry, that looks like a positive there, it's a negative. Multiplying by negative 2 means that we get y minus 3 is negative 6 over x plus 2. And if I add that 3, y equals negative 6 over x plus 2 plus 3. And that's the equation of the image. Now example 6 is really just to show you that this can also be done using a functions approach. So just to summarize this video, I'm going to do a quick example for you using the functions approach. If we were dilated by a factor of 2 from the x, so factor 2 from the x, then f of x should become 2 f of x. If we were reflected in the x-axis, then 2f of x should become negative 2 f of x. And 1 unit in the positive y, well, negative 2 f of x should become negative 2 f of x plus 1. And pi on 4 along the x-axis, so let's say that's also positive direction, then negative 2 f of x plus 1 should become negative 2 f of x minus pi on 4 plus 1. Now my pre-image was y equals cosine of x, so now y is going to equal negative 2 times the function, which in my case is the cosine. It's not going to be x, it's going to be x minus pi on 4, because there's that translation. And to say that it was shifted up, we've got our plus 1. So you could try this now if you like, using the matrix approach, but keep in mind that these are related, and usually it's going to be your choice. There are multiple choice questions on the exam which strictly are matrix approaches, and there's always going to be parts of extended response and application questions that may well include a matrix equation, so it's important to know both. But usually, if you are asked to apply a sequence of transformations, you could take your pick on which approach you prefer. For the summary of this video, just remember that if you see a matrix equation, you can describe the sequence of transformations exactly as you see fit. Your method for finding the image will be to resolve the matrix equation, let x equal x dash, y equal y dash, so in other words, we're going to solve for x and y, and then sub those into your pre-image and solve for your image.